let us look at a few applications that we have worked on from our own research projects. We will look at detection of the spinal canal, and this will come up a little later in my seminar on 3D image processing for landmarking. I'll show some of this again later. Spine, spinal cord, and spinal canal, they are important landmarks in procedures for image-guided surgery, therapy, radiation therapy, and so on. Also in the design of atlases and design of algorithms to detect, segment other organs, they can form as references. With reference to the spine, you can locate other organs and structures in the body. In one of our projects on the detection and segmentation of the tumor due to neuroblastoma, I showed that tumor in the abdomen earlier, we found the spinal canal was observed to interfere in the segmentation process. That is, when we were growing the region for the tumor, it would go into the spinal canal. So in this manner, we identified certain structures that were causing problems in segmentation of the tumor. In order to improve the segmentation of the tumor, we said, let's identify these other structures and remove them. There's an old story. I even have some pictures to show that. There was somebody who went and saw some beautiful sculptures of elephants in our temples, stone sculptures of elephants, and went and asked the sculptor who does that, how do you carve these beautiful elephants? And he said, well, I take a big rock and I remove everything that is not an elephant. So that is removing structures. That doesn't help us. So remove things that are not what you want to find. So remove everything that is not the tumor. That's what the radiologist also told us. We asked, well, I can't find this, I can't see the tumor, how do you find it? He said, well, this is the kidney, remove it, this is the liver, and so on. What remains is something suspicious. So there is a process of elimination also that could help. So we said, let us detect all these other organs that are causing problems, but they're also important as landmarks. And this will come up later again. Okay, one thing is missing here. The section of the spinal canal, not the whole spine, the spinal canal inside the vertebral body is circular in this region. So in the neuroblastoma cases, the images were of the abdomen and partly into the pelvic cavity and the thorax, but not in the main chest area or the neck area. There, in the neck area, the spinal canal becomes almost triangular in shape, and in the chest area it could change shape a little bit, but in the abdominal area it is mainly circular. As you go lower into the pelvic area, again the shape changes. So depending on the area of the part of the body where you are, there are some parts where the shape is known, and here it is a circle. So we said, let's find the circle, but we need to get that circle boundary. So the initializing seeds for region growing procedure were obtained using this procedure. So we said we need to get to the spine, but we will come from outside. The outer region of the CT volume containing the materials outside the patient's body, the whatever blanket and other things, they were all segmented. You start from the outer boundary of the image and grow inwards, allow some variation, come up to the skin. The advantage in using CT images is you know the Hounsfield unit values for all of these structures. They're tabulated and there are references that give you with and without contrast medium. So I'll give you those numbers later on or as we go. The CT volume was then thresholded at 800 Hounsfield units to detect the high density bone structures, and we remove those. All boxes not within 8 millimeters from the inner boundary of the peripheral fat layer were rejected. And then regions were growing using each remaining voxel, and we got the bone volume. For the bone, it was 800 plus minus 2 sigma, with sigma being 103 Hounsfield units. And then we cropped that to limit the scope of further analysis. Initially, just the geometry of the image was used, but later on I'll show you a better procedure. This was done by one of my students, and another student modified it and improved it. So the width and height of the image were taken. The patient is always lying on the back, and the patient is centered, so the spine has to be there based on the imaging geometry. So we cut that portion and take the bone volume in that area. To detect the bone volume is not a problem. As I said, it's high density, so that threshold of 800 plus minus 2, we need to take that into account in considering adults versus pediatric patients. Here we had pediatric patients. So some of these are arbitrary limits. The first 13% and 20 slices and so on. So we removed all of that in subsequent algorithms, so I won't go into that detail. So what I want to show you is more towards, let me go here. Let me show the picture since we're coming to the end of the day, and I'll go to the background later. So here is a CT image, and this was the cropped area. So in most cases it worked, these constraints worked. And of this cropped area, we find the edges, the edge map of the bone volume. The bone region in 3D was grown earlier. And now you see a nice circle, almost nice circle. So to this binary map, we apply the Huff transform. We have a certain range of circles. I'll go back and give some of those parameters. And then in the Huff space, there are many circles, as I said earlier, like this. This is another, in this case, we got this bone edge map. This is broken here, but we have half of a circle here. So that is the circle we want, even though it is broken. The Huff space, for every point here, you draw a circle of the radius of that parameter slice. So you see all of those. And this is for 15, radius 15 pixels, 17, 19 pixels. Not full. Still, there are some 50, 60, maybe 70 pixels. Not full. Still, there are some 50, 60, maybe 70 pixels there. Here you may have a total of 40 pixels maybe. But that's the circle I want. So it's not the first peak. It could be the second or third peak. So find a number of those peaks. How many of peaks you can find in the Huff space, or the top so many, 10, let's say. So here we have the 4 circles corresponding to the first 4 peaks drawn. You see one of the circles is fitting that. So now which one do you want? Fortunately, one is fitting this also. So we check what is inside each circle. This circle has high density bone. We know the Hounsfield unit for this and that. So we reject that. So in this manner, find the average density or Hounsfield unit value in each of these circles, and then select the circle that meets all of your conditions. In this case, there was no problem. The first circle was the final circle. The circle has a radius of 6.6 millimeter. So that was easily detected. So let's go back and look at some conditions here. So note that the vertebral column is not continuous but made up of interlocking segments. So the bone edge map could be sparse, as I showed. The radius in the Huff space was limited to 6 to 10 millimeters, pediatric cases. So the global maximum in the Huff space may not always give you the desired circle. So get the top view and then ask, is this circle what I want? So CT values used as constraints: bone marrow plus 142 Hounsfield units, sigma 48. Spinal canal 30 Hounsfield units. The actual spine, the bone will be much, much higher. So if the center of the circle corresponding to the Huff space maximum was not within that specified Hounsfield unit range, it was rejected. And the circle corresponding to the next maximum in the Huff space was evaluated in the same manner until a suitable circle was detected. Now, about detection of seed pixels, you asked. The center of this circle was taken, of each circle detected, in all these slices. In each slice you get a circle. Take the center and a few pixels around that as your seed and compute and in 3D. So the centers of the circles detected were used as seed voxels, and in subsequent algorithms we chose a neighborhood like a tube connecting all the centers and like a 3x3, I don't remember, I'll show that later on. So we get a number of voxels, volume elements from 3D data set that are in the middle of the spinal column, in the spinal canal. The mean and standard deviation were estimated using, it says here, 7 by 7 by 2 neighborhood, or for each of those slices. So then we got not only all the seed pixels or voxels, but also the mean and standard deviation of the spinal canal for that patient. Initially we had some reference from some other publication or from our database. Using this procedure we have a number of seed voxels and the statistics for that particular spinal canal. Then we do fuzzy region growing using all of them. And then we get the spinal canal in 3D. This is the bone structure that was segmented earlier to find the spinal column. So for this patient, that sort of brown, reddish brown, that is a spinal canal in 3D, obtained by region growing. But the seeds were detected in this manner. So the circle was not used for any other purpose. The circle was thrown out, we just want the center, and take a neighborhood around the center in 3D. Okay? I'll show this again later with some refinement and other landmarks. Detection of the breast boundary in mammograms has been a big research topic. Not anymore, but in the 80s, 90s, 2000, it was a big topic. In a mammogram, you have the X-ray projection image of the breast, but also there are some markers placed outside to indicate left, right imaging parameters, and not imaging parameters, but some other labels are there. MLO, CC for craniocaudal and mediolateral oblique views. Some labels are placed, and their shadows also appear in the image. We want to reject them. We want to get everything outside the image, outside the breast area, and get the breast boundary and then compute statistics within that area. So no point in computing statistics over using all the image pixels with background and other things. So Ricardo Ferrari from Brazil did his PhD work with me and his supervisors in Brazil on this topic. So first we started with the traditional active contour model or snakes, and he included this active deformable contour model. I'll go through the procedure. The image contrast is first enhanced just by taking log. And to avoid taking log of 0, you just add 1. That's not a big deal. We have seen some pictures like that, the mammogram and the log. So now the edge comes out very clearly, better than in the original. So we can't see the edge here. The edge is seen clearly. These are all the labels, and you don't want all of this black background. So let me go back to this stage 1. Okay. Let me go and find stage 2. Where is that? Stage 2. A binarization procedure is applied using the Lloyd-Max quantization method that I described earlier, right at the beginning. You could use any quantization technique. Spurious details generated by the binarization step are removed by using a morphological opening operator with a structuring cell element of diameter 7 pixels. I haven't covered morphological image processing. I'll give you a brief description of that later. Nowadays it's commonly used, so I didn't include that in the preceding matter. And then an approximate contour is extracted by using the chain coding method. You will see chain coding later. So some of these applications have been put in this chapter, but some methods will come later. So the starting point of this approximate curve is obtained by following the horizontal paths starting from the centroid of the image, right in the middle, towards the chest wall until a background pixel is found. So this avoids selecting an initial boundary points from the artifacts of patient labels. You don't want to start with a wrong pixel on the boundary. So you go towards the chest wall and you get a correct boundary point there. 4 control points are determined. I'll show that later on automatically. And then pixels along lines of length 40 pixels are identified at each point of the approximate skin air boundary in the original image in the direction normal to the boundary. So you draw perpendiculars to the tangent at every point along the contour. That's the initial contour. We are going to adjust that contour. The gray level histogram of the pixels along each normal line is computed, and the skin air intersection, that is the boundary, is defined as the first pixel while going from inside the breast towards the outside. That has the gray level associated with the maximum value in the histogram. So that histogram looks like this. And these are values inside the breast, and then outside the breast it's some noise variation. And you want to catch that point. That's the profile. And this is the histogram of those pixels. And then the traditional snake's model is applied to define the true boundary. That's a further manipulation or modification of that contour. So the contour obtained up to this stage is put as the input to the traditional parametric active contour or snake's model, which starts with this. And the contour is moved through the spatial domain of the image to minimize some functional of energy. And one of them is defined like this: 0 to 1 around the boundary, alpha v prime s for beta v double prime s. Vs is the contour. So this is the internal energy, and then external energy that depends upon the gradient in the image. So image gradient is brought in. This is internal to the contour or the so-called snake. So the contour is expected to maintain certain continuity and rigidity, and it should fit to certain gradient values or high gradient values in the image. So that is how the contour is adjusted. So alpha and beta are weighting parameters that control the tension and rigidity of the so-called snake. V prime s and V double prime s are the first and second derivatives of Vs, where Vs indicates the representation of the contour, and S is the distance along the contour normalized to the range 0 to 1. So 0 to 1 means going around the contour once. So it is a continuous representation, not pixel by pixel. The external energy is based on the image, and typically a gradient measure such as this nabla, whatever, however you compute some gradient measure. That need not be specified. It depends on how you want to implement it. Could be some gradient like Privet or Sobel or some other gradient, and then you use that in the other expression we saw earlier. And some values for alpha and beta need to be determined based on your application. So let's go back and look at these results in various steps. So that's the original mammogram, log, that's the initial contour, and then the refinement, and that's the initial contour. These are the points that are automatically marked at the top, left and top right, and where the contour intersects this chest wall. This is the chest wall. This is a mediolateral oblique mammogram, so that is the pectoral muscle, which has an almost straight line edge, but we will talk about that later. So this is the initial breast boundary. And then we draw perpendiculars or normals to the breast boundary at every pixel and analyze the variation coming from inside the breast to the outside. So this may not be the best position. So by taking pixel values along the normal, we analyze again and ask, should I move this in or out and adjust it? all the way around, not here. But that should work anyway. And using that histogram, this is the next level of the curve. Now there is some smoothness put in here. But look at this result. That is where the nipple is. It was obtained here, and then it got lost here. So there is some give and take. You may lose some details. H is the end, final boundary with the SNC's algorithm. So overall smoothness has been imposed. You impose too much smoothness, then the nipple which has the discontinuity will be lost. So you need to adjust the parameters of your algorithm so that you don't lose important details. Or you may say, okay, this is the boundary, I'll take this and I'll detect the nipple separately. And there are many algorithms to detect the nipple separately. And we have some of our own, so let this go and do that separately. Well, this is not a bad boundary. So that was the procedure. So we analyzed some 66 images, and there are some problems with this. This label came too close, and that was included. And we need a better method. So Ricardo came up with another technique called adaptive active deformable contour model to make it adaptive. So it includes what he called a balloon force in the energy formulation to minimize the influence of the initial contour on the convergence of the algorithm. The external energy is also designed to be locally adaptive. So we get an initial contour, and this approximate contour we want to Vn is a collection of, now it is discrete, xi, yi, I going on to n. Those are the points that are obtained by sampling the approximate contour from the previous method. The previous method gave something, and that we are further refining. So this is used as the initial contour in the new algorithm. And we are using only 10% of the total number of points. We are not using all of those points. So that is the contour, and these are the points selected. The total energy now is internal energy plus external energy like before. The internal energy has a continuity energy and a balloon energy, a linear combination of the two. So the energy component ensures a stable shape for the contour and constraints to keep constant the distance between the points in the contour. So the parameters were initially set to just 1. For each element Mn in the neighborhood of a pixel Vi on those on the discrete sampled contour, the continuity term is computed in this manner: 1 over Lv Pmn Vi, that is a pixel close to that, rho Vi minus 1 Vi plus 1 here. So these are the points on the contour, and we take a neighborhood, a 7 by 7 neighborhood around this Vi. These are the 3 points on the contour that is input to this algorithm. This is region inside the contour, and that is outside. The active contour, now we are considering movement of that point. Where should that be located or relocated? And this is P11 to P77 in that neighborhood of that pixel. That is one of those sampled points. So this Lv is Vi plus 1 minus Vi square in that neighborhood. Pmn Vi is a point in the image at the position Mn in that 7 by 7 neighborhood of Vi, and rho is 2 cos 2 pi over n inverse, is a constant factor. So the balloon force is used to force the expansion of the initial contour towards the breast boundary. and that was made adaptive to the magnitude of the image gradient, causing the contour to expand in homogeneous regions and faster and slower near the breast boundary. The balloon term was defined in this manner. Ni is the normal vector, Vi minus P Mn Vi. I think another picture comes up here. Yeah. So this is the initial contour, and it is expanded towards the final contour. You have a tangent and a normal. And if it is a region with uniform intensity, you keep pushing it. Ni is the outward unit normal vector at that point Vi as a dot product, and Ni is by rotating the vector, that is the tangent. Ti is the tangent, and rotated by 90 degrees to get the normal. These are points along the contour, so you are finding the tangent. The external energy is based upon the magnitude and direction of the image gradient, which is this gradient on the image at that location Vi, and it is given the vectorial form by attaching with this. You're taking the dot product of the normal with this. So the direction of the image gradient is used to avoid attraction of the contour by edges that may be located near the true breast boundary, like those ID marks and other artifacts. So this is the pixel that needs to be corrected, and that is the normal direction, and the scope of modification is this. And the true edge in the image is there, and the contour is here. You want to push it towards that. So in this case it worked well. The contour went through here instead of including that object in this manner. So minimization of the energy functionals, the continuity is defined as this function at Vi ECMN, ECmin, and the others, they will come in a moment. The balloon factor is defined in this manner. I won't read all these equations, you can read them later on. The external energy is based upon the difference in this manner, like a derivative. I'll skip some of these definitions. The curvature at each point is obtained using these vectors joining two neighboring contour elements, Vi plus 1 time here. So we get this contour, and it is keeping these objects out. In this work, Riccardo Ferrari, he tested the methods with about 84 images, different number of images for different algorithms here. And these are mediolateral oblique views with 200 micrometer sampling interval and 8-bit gray level quantization from the MAIAS database, that is a public database. The images were reduced to 256 square for just detection of the breast boundary. And then the results were mapped to the original mammograms. And the results were evaluated by two radiologists. They ranked it. The display doesn't matter. We also evaluated in terms of false positive and false negative pixels. Number of false positive pixels identified with respect to the contours drawn by the radiologist. How many pixels did we miss and how many pixels did we add? The breast boundaries were all drawn by the radiologist, and the breast boundaries detected by the methods were also checked by them visually. So the false positive and false negative were less than 0.5% for 33 of the images. 38 images had between 0.15 and 1%. So some examples here. That's the detected boundary. In this case, the nipple has been detected. Well, it's clear. Another example. Another example. And we'll stop there. The evaluation was done by giving the detected contour to the radiologist, and they're ranked. And we also measured the distance using mean distance to the closest point. And I'll describe those measures later on in the context of other detection methods as to how to compare quantitatively a detected contour with a reference contour given by the radiologist or the medical expert. The next application is detection of the pectoral muscle, which I showed in these MLO mammograms, but we will take that up tomorrow, 4 o'clock. Sorry, I rushed through some of these, but I don't want to read all the equations. Sometimes I feel reading all the equations doesn't make much sense. I'll show the pictures and explain what is happening. Some of the equations describe the parameters of the methods, and you could read those yourself later from the notes. Okay, I went through a little fast to keep track of the time, but do you have any quick questions? Any comments? No? Do you have any comments?
Remarks, that's all.